What are the rules behind that? You kind of see some of that regulation and rules when you look at nomenclature, because we look at naming our compounds based on covalent bonds versus ionic bonds. And ultimately what determines that comes back to this concept of electronegativity. Okay? And it's a strict comparison between our atoms and their electronegativities. We've come up with some kind of shortcuts to get through that, but it's ultimately, it really does rooted back in the strict electronegativity differences. Okay? So we'll keep coming back to this idea of electronegativity and how does that apply to our bonds. So, chemical bonding. What makes a bond? So if I take these two red spheres and I bring them near each other, what makes that now a bond that's connecting those two?
Sharing electrons?
What does this sphere represent?
The electron cloud.
It's the electron cloud. Okay, so it's each of our atoms, it's the electron cloud around each of those. What ends up happening when I bring those two spheres close to each other?
They begin to share electrons.
Like a little, I should probably use a different color than red, but like a Venn diagram, there's an area where they overlap. That area where they overlap is now the bond. Okay? So we're looking at the sharing of electrons, and the extent to which we share determines what type of bond we have, which brings up the next question. Are all bonds going to be the same? Would I expect the same bond for two red spheres as I would for a white and a green sphere? Okay, probably not. We're looking at different atoms. Those atoms are holding their electrons to differing extents. Their electrons are at different energy levels. We're going to expect to see variances in what determines a bond. Okay? So, what things classify our bonds? So we've got different types. We've got ionic bonds and covalent bonds, which is what we pick up kind of out of chapter 6. And the rule of thumb that we threw at you for those two was that an ionic bond is a metal and a nonmetal. Right? And a covalent bond is two nonmetals. Well, if we think back and compare to electronegativity, which means I might have to go back a couple slides. Yep, let's go back a couple slides. Or a couple more. Geez, it's way back there. We look at our electronegativity. An ionic bond was a metal and a nonmetal. What is fluorine? Fluorine is a nonmetal. What is cesium? A metal. So what are we looking at when we put those two next to each other? We would expect what type of a bond? Ionic bond, because we have a metal and a nonmetal. Okay. What happens if I took fluorine and I bond it to fluorine? We got a covalent bond, okay? Two nonmetals. What's happening with our electronegativities? I know this is not easy to see, but for those of you up close can maybe help us out. What's the electronegativity for fluorine? Okay, as a big help out, electronegativity for fluorine is, just drew it on there, 4.0. Okay, it is not found on your periodic table. Okay, your electronegativities are not summarized there. You'd have to actually look up the electronegativities. What is the electronegativity for cesium? .7. What is the difference in electronegativity between these two? Is it big or small?
Big.
It's big. It's as big as we can possibly get. Fluorine is our most electronegative. Cesium is our least. So that difference in electronegativity is so big, okay, that we classify that type of interaction where it's a really big difference as an ionic bond. So if we take any metal and we bond it to any nonmetal, we see that large difference. Okay, why? All of your nonmetals have higher electronegativities than your metals. So pretty much any comparison where we bring in a metal and a nonmetal, we're going to have this big difference in electronegativity. What happens if I bond fluorine to fluorine?
Small difference. Well, no difference.
There is no difference in electronegativity because one fluorine atom has a 4 and the other fluorine atom has a 4 electronegativity. No difference, equal sharing of electrons. So if we now have, no difference in electronegativity. So no difference versus a big difference. We could take this a step further into what our definition of electronegativity was. It's the ability for an atom to take bonding electrons from another atom. So what happens when we bond fluorine to cesium?
Fluorine takes all its...
Fluorine is going to take all of the electrons away from cesium, or all the bonding electrons. Well, if fluorine takes those electrons, what charge does it become?
Plus whatever.
Negative. So let's define what your plus whatever. What's the whatever?
Negative.
Whatever are electrons which have negative charge. So yes, it is plus a negative, which gives us a charge of negative. What happens to the cesium? It's going to become positive because what happened to it? It lost electrons. So we have the loss, which is a mathematical symbol of minus, a negative charge, a minus times a minus, positive. There's our positive value for our cesium. What happens when we bond fluorine to fluorine? Both fluorines are now really pulling on the electrons. Which one pulls tighter on the electrons?
Neither. It's neutral, right?
Neither pulls harder on the electrons because they have the exact same electronegativity. Which means where do those electrons spend all of their time? So if we draw out our two molecules, we got our cesium and our fluoride. Fluoride takes our electrons, holds onto it so it becomes negative and the cesium becomes positive. And we'll draw two electrons as dots, which we'll talk about in a little bit too. If we look at fluorine to fluorine, where do those two electrons spend their time? Which atom takes them? Neither. So where do the electrons exist? Exactly in between the two atoms. So if we go through and try and compare this, in our cesium fluoride case, we have an unequal, whoops, red's a bad color on that, an unequal sharing of electrons. Electrons, right? And in the other case, what do we have? An equal sharing of electrons. Okay? So that's kind of our big delineation, is just looking at those electronegativities and trying to decide how they're sharing those electrons. And that allows us to decide, are they ionic bonds or covalent bonds? Okay? Yes?
Do we ever have to do like actual calculations with this where I have to do sig figs and stuff?
Sig figs? No, absolutely not. As far as calculations, kind of, sort of, we'll talk about how we can get away without doing calculations. I'm not a fan of numbers, so I try and find any way that we can cheat out of them. Okay? So are all non-metal bonds equivalent? Okay, so with our ionic bonds, we might go through and say, okay, they're all roughly ionic bonds. But are all covalent bonds, where we take two non-metals, exactly the same? Okay, as an example, we've got H2O versus HCl. H2O is commonly known as? HCl commonly known as? Hydrochloric acid. I know we're missing the AQ, but let's just go based off of your general understanding. Do we expect the bond between the hydrogen and the oxygen to act exactly the same as the hydrogen and the chlorine? According to our definition, we say, yeah. Is that true? No, there is a drastic difference between those. Hence, we don't shower in hydrochloric acid. Okay? There's massive, massive changes between those two molecules. Those massive changes aren't described by just separating into covalent bonds and ionic bonds. Okay? So there has to be some gradation in between, and that gradation is what we're looking at when we look at our types of bonds. Okay? So in our ionic bonds, we're strictly looking at, and this is how your textbook describes it, I'm not a big fan of it, but it's looking at a transfer of electrons. Okay, we take the electrons that were shared in the bond, and those electrons now are no longer shared, they are transferred to one atom over the other. Well, which atom is going to accept those electrons? The one with the highest electronegativity. Between a metal and a nonmetal, which element has the higher electronegativity? Non-metals. So our nonmetal takes the electrons. If it takes the electrons, it becomes negatively charged, and we refer to that as an ion. An ion. Yeah, that was probably the appropriate laughter. What happens to our metal? Well, the metal has now lost the electrons, is now positively charged. We refer to that as a cation. Okay? Because we now have these positive and negative charges, what ends up happening when we look at an extended structure? Okay, well, what we get is what's shown here. We get this very regular pattern of positive, negative, positive, negative, positive, negative. Why?
Because science.
I saw you mouthing something. What was that? Balance. I don't want to quite go as far as symmetry, but that's not a bad idea. Charge. Are charged things stable? No. So what do we need to put near charged things? Other charged things to balance them out. So what happens? We put a positive near a negative. And all the atoms around that positive should be negatively charged. And we end up with these very regular repeats. Okay? So if we were going to look at a molecule of any ionic compound, it gets a bit weird because we don't have a molecule of sodium chloride. We've got this big, massive, extensive structure. Okay? Our pseudo-cheat way around that is we then reduce that to the smallest whole number ratio, and we then call that a formula unit. For all intents and purposes, it's a molecule, okay? Because we're looking at that bond connecting those atoms. Okay? With our ionic compounds, what happens to our radius for each of those atoms? So one thing we can do is look at our sodium atom versus our chloride atom. So if we look at sodium and chloride on our periodic table, so ignore the picture, because maybe the picture is misleading. Which atom is bigger, sodium or chlorine on our periodic table? As a hint, the picture is not misleading. Sodium is bigger. Why is sodium bigger than chlorine? It has a greater atomic radius. That is defining it by defining it, using the definition as the definition, so that doesn't quite work. Why is sodium bigger? Chlorine has more electrons. Shouldn't it be bigger? Where are those electrons being added as we go from sodium to chlorine? The same energy level, which means distance from the nucleus is the same, completely identical. Within a row, we would not expect a change in radius. Why does chlorine get a little bit smaller than sodium? What else changes? The number of protons in the nucleus gets larger. So we end up with a stronger positive charge. If we put the electrons the exact same distance away, those electrons are going to get pulled ever so slightly tighter in. And what we end up seeing as we move left to right on our periodic table is that size decreases. Okay? And it all has to do with those electron configurations. So we would expect this relationship, sodium to be bigger than chloride. But what happens when sodium with respect to chlorine as an atom? What happens if I now go to making a bond? Okay. Chlorine, being much more electronegative than sodium, does what? It takes an electron away from sodium. So if sodium loses an electron, what should happen to it?
Shrinks.
Why should it get smaller?
Because its electron cloud shrinks. Because it loses
It has
electrons.
less electrons, it should shrink a little bit. Okay, how much should it shrink? A lot or a little?
Level that depends on how many electrons we take.
Why do you say a level?
Because it's taking the outermost electron from the vacuum.
And if we, not from the vacuum.
Vacuum, just
If we take the outermost electron from sodium, which has an electron configuration of 3s1, we remove that electron. Where are our electrons now? In the second energy level. That's a full energy level difference. Okay, we would expect a pretty massive change for jumping energy levels. Why else should it shrink? There's now a larger ratio of protons to electrons. So as we go through to make that bond, that sodium atom should really drastically shrink down in size. Okay? Because you now drop to a lower energy level and your balance between protons and electrons is now out of whack. The protons can actually hold those electrons, few remaining electrons, even tighter. So we would expect our radius for our sodium to get even smaller. What happens to the chloride?
Bigger.
Okay, it gets bigger. We're just adding one electron, right? So we'd be comparing chlorine to argon as far as electron clouds go. Everybody agree with that? Which is bigger, chlorine or argon?
But we're not adding protons to chlorine.
Come back to that. Which is bigger, chlorine or argon?
Chlorine.
Chlorine. So why are we saying chloride should get bigger if it's starting to look like argon? What was your explanation?
We're not adding protons to the electrons we're talking about.
We add an electron, but we don't increase the positive charge. So we're putting that electron in the same energy level, but we're now not providing anything to balance out that electron, which means the electron will now exist further from the nucleus. So what happens to the radius of your chloride? It should get bigger. Okay? This ends up getting translated to a larger scale on now trying to compare ionic radii across the periodic table. So what happens is you go left to right with the ion versus up to down. Okay? You could potentially look at those strict trends. It becomes a little bit trickier than that because you're looking at putting electrons in different orbitals. The best way to evaluate ionic radii is to compare exactly what you're asked to compare. So if I asked you to compare the lithium ion to the beryllium ion, look at those electron configurations and see what happens when it goes through and does that exchange. Yes?
So based on those numbers at the bottom, they essentially switch radii?
They essentially switch radii, yeah. Okay? That's really just kind of an approximation. Okay? Questions on that? Yes?
So is it like using electronegativity? I'm not.
So you aren't using electronegativity. Okay? The only thing we're using electronegativity for is to say that the electrons were transferred. Once the electrons have been transferred, we're now looking at the electron configuration. Okay, so let's look at the electron configurations, write it out for chlorine atom. What's the electron configuration for a chlorine atom? Feel free, start writing. Electron configuration, chlorine atom. Where's your first electron go? I like S as your first electron. That's your ground state. I need more detail. It's not just S. The 1s orbital. How many electrons fit? 2. That only gets me up to the electron configuration for helium. What do I do now? 2s2. Up to 2p chlorine atom. Chlorine atom.
17.
Which column is the chlorine atom in?
17.
Oh, the P.
It's in the P. How many electrons? Okay, I'm hearing 6 a lot. Let's total this up. 2 plus 2 plus 6 gets you? Oh, never mind. I know why you're saying 6. You're right. I'm wrong. I'm an idiot. You're good. Let's switch that up. Pretend I didn't say that. 2p6. You're right. Next place. Shh. 3s. 2. Now 3p. Yeah. I'm an idiot. Deal with it. 3p5. There's our chlorine atom. Okay? Now if we wanted to check this, just in case you haven't seen this yet, 2 plus 2 is 4, 6 plus 2, 8, 5, 4 and 5 is 9 plus 8. How many electrons should we have? 17. So it adds up right. All right, just as a quick check. I can't believe I did that. Okay, chloride. Electron configuration for a chloride.
Question, could you use neon as part of that?
I'm going to do that for the chloride, actually. So what we can go through and do is instead of writing all of that, whoops, dang it. I should just give up and walk out. You guys can take over. Instead of writing all that 1s, 2s junk, we can go through and call that the electron configuration for neon. And then we really just have 3s2, 3p5. Right? If we go to the chloride ion, what's different between chloride versus chlorine? If you change the number of protons, is it chlorine? No, we can't change the protons. What do we have? One extra electron. So if we go through and look at our configuration, we would have neon, 3s2, 3p6.
And it's incorrect to write argon there? The electron
So, could we also go through and show this as the electron configuration for argon? Absolutely fair game. There's a reason I'm not doing it right now. Okay? And the reason is we want to see that we've added that extra electron, because what we're trying to do is determine what's happening with our radii. Okay? So what happened is we go from our chlorine atom to our chloride atom. You've increased the amount of electrons. So theoretically, what should happen to size? It should get bigger. That's what you're comparing. Okay? This same theory is what we use to compare, say, nitrogen to oxygen. But in the nitrogen to oxygen case, we notice that the atom got smaller. Here it's getting bigger. Why is it getting bigger? What was that? We're not changing the protons. So as we move from chlorine atom to chloride ion, we don't change the number of protons, which means there's less of a pull from the nucleus to keep those electrons tied in. The size of the chloride gets bigger. Okay? So far, so good. Does that answer your question? You understand that a little bit better now? Okay. So within an ionic radii question, what we could ask is which of the following is bigger or smaller? Okay, so one case could be chlorine atom to chloride ion. If you look at the electron configurations, you have a way to answer that based off of everything we've talked about. Okay. If you want to go through and memorize a trend, I'm sure the textbook gives you something to memorize. I can tell you right now, I do not have it memorized, and I might be able to derive it on the fly, but I'm hoping you don't ask me to. Seriously? It should shrink for the column 1 and column 2s because you're losing more electrons. And as you move to the p orbitals, or the p block, it should get progressively smaller as well, actually. Because when you move to your ions, nitride, it carries 3 electrons, versus oxygen carrying only 2, versus fluorine carrying only 1. So we would predict the nitrogen and the oxide ions to be bigger than your halide ions. So it does look like it shrinks as you go left to right. Okay. Down a column, what should happen? That's actually going to be a little bit more challenging. Lithium ion, okay, has the electron configuration for helium. Sodium ion has the electron configuration for neon. So our size pattern is still probably going to get bigger as we move down, but we're still going to be smaller than if we were the original atom. Okay. Covalent bonds. In a covalent bond, we typically classify this as having the exact same atoms, which means your difference in electronegativity is 0. We are sharing electrons between the atoms. Okay? So our electrons from one nitrogen or one red sphere are equally sharing with the electrons from the other red sphere. And that equal sharing now kind of changes our bond properties. Okay? One big reason that changes, do we have a cation and an anion? No, it's equal sharing of electrons. Neither one carries a positive or negative charge. So right off the bat, we're going to have a drastic difference between our ionic bond characteristics and our covalent bond characteristics. Okay? We could go through and start to evaluate something else. In this case, what we'll look at is bond length. Okay? We won't look at ionic radii. Why not ionic radii? Because there aren't ions. If there's no ions, you can't have an ionic radius. Okay? The atoms themselves won't change size either because they're neither gaining nor losing electrons. So the only thing that we can really compare is then the bond length. So the bond length is going to represent the distance between the nuclei of our atoms. Okay? What should that bond length be? So if we look here, do we have a bond? No. Okay, so if I measure the distance of one radius, the other radius, and the space in between, I could get the total distance between those nuclei. But there's no bond. When do I have a bond?
When they smush together.
Kind of the right idea. When what smushes together?
When they're clouds smush together.
When the electron clouds smush together. I can't believe I'm saying smush. Our electron clouds have smushed. Okay? What does that mean is going to happen to the distance between those nuclei? Should it be just as simple as the radius of one and the radius of the other?
Yes.
Okay. You take two spheres, right? If I just take to the middle of my hand, there's the radius of one to the radius of the other. Have my hands overlapped yet?
No.
When do they overlap? Oh, that looks kind of ugly, but it's close enough. Okay. What happens to the distance to the center of my hand versus just looking at the outer spheres? Okay. When we smush them together, the distance between those nuclei is less than the sum of the radii, because that's the only way your electron clouds overlap. Okay. If we use just the radii distances, we aren't going to get exactly the same thing. So if we look at the radius for a hydrogen atom, it's 0.037. We can worry about the units later. For a chlorine atom, it's 0.099. If we just add the radii and bring those two spheres so they just barely touch each other, the distance between the nuclei would just be the sum, 0.136. But if we do that, do the electron clouds overlap?
No.
No. And if they don't overlap, we can't have a bond, or at least a covalent bond. So what has to happen?
Have to overlap.
They have to overlap. To do that, we must smush them, which means what happens to the radius, or the distance between our nuclei? It gets a little bit
Small.
smaller. So your bond length in a covalent bond will actually be a little bit smaller than the sum of the radii. Okay? And that's because we need those electron clouds to overlap with each other and interact. If they don't interact, we can't get that covalent bond. We don't have anything to evaluate. We wouldn't be looking at a bond length anymore because they never formed the bond. Kind of makes sense?
What kind of an overlap can they get? Can they ever eclipse each other? What, no, like.
So I was going to ask that question. So steal my thunder. How close can they get? Okay, that's a good question. Are you responsible for that? No. What's going to control how close they get? What's happening in that overlap is we're taking the electrons from the hydrogen atom and they start to see the nucleus of the chlorine atom. So if they see that positive nucleus, the electrons start to move towards that nucleus and become shared. And the electrons from the chlorine atom see the nucleus of the hydrogen atom. So those start to jump across and share. But what happens is we bring those atoms closer and closer to each other. We start to bring what else closer and closer to each other?
Nuclei.
The nuclei. What happens when a nucleus sees another nucleus?
Separates.
It separates out and it repels. So there is going to be a perfect distance where just the electrons are arcing between each other and the nuclei have not quite seen each other. Mathematically, what does that quantify to? Who knows? Who cares? We don't need to worry about it. Okay? All you need to know is that bond length is a little bit less than the sum of the radii. Make sense? Bond energy. I hate bond energy. Okay? As soon as you bring in energy, you got positives and negatives and it makes a big mess. So let's think about the bond energy here. Okay, so a reaction can absorb energy or it could release energy. That's our theory here. So if we take a look at this reaction, let's assume it occurs. Is that safe to assume? Is it safe to assume bonds form?
Yeah.
Why is that safe to assume?
Without bonds, we wouldn't have water.
Without bonds, we wouldn't have water. Without bonds, we wouldn't have
Hydrochloric acid.
hydrochloric acid. Without bonds, we wouldn't have
Alcohol?
ourselves, okay, or tables or pencils or anything. Everything would be just free atoms.
We wouldn't have coffee.
No bonds, and we wouldn't have coffee.
It's not like with living.
Sorry. Okay, I can't supply that right now. So, we would assume that we should form that bond. Which type of reaction is easier to occur? One that absorbs energy or one that releases energy? I know that's a hard
Absorbs.
question. We haven't really officially talked about
One
it.
that absorbs.
It's going to be releasing energy. Okay? If it absorbs energy, then we have to supply that energy to have a reaction occur. If we just have those two atoms come near each other, then nothing would happen. We'd have to constantly be putting energy into our system to get anything to happen. Okay? If we look at it releasing energy, what happens? I bring those two atoms near each other and they go, oh, yep, let's form a bond. Boom. There's the release of energy. So I would predict in the formation of a bond that energy should be a product. Okay?
Like ADP almost?
Ish. Yeah. I'm not sure I want to go to that secondary issue. Let's just keep it simple. So we release that energy. So now we come up with a couple ways that we want to explain this. Okay? So in the process of forming a bond, we can say, number one, energy was
Released.
released. Okay, we can't say it was created. Why was it not created?
I stopped myself.
We can't create or destroy energy. Where did the energy come from?
Within the bond.
The higher energy of the atoms, okay, those electrons. Okay? And within an atom, what's happening when we form that bond is we're taking those electrons at high energy and we're now sharing them with another positive. What does that do to the negative charge?
Diminishes it.
It diminishes it, which makes it more neutral, which makes it lower in energy. Okay? So we're taking those electrons at very high energy states and we're now actually dropping them in low energy states because of making that bond. So our energy is released in the process of making that bond. I want to break a bond. What do I have to do?
Put in the radius.
I need to add energy to the reaction, or I could say energy is consumed. Okay? All we're doing is now shifting our perspective on what's happening. I'd be changing the reaction to go the other direction. To go this way, where does the energy term need to show up? Well,
Between the two.
the same place it showed up in the beginning. In the beginning, it showed up with the two nitrogens, our two N's. So remember when we did our conversions and I said, where does the number show up? We kept getting top and bottom and I kept saying, I don't accept that answer. Where does our energy term show up? With our bond. Which means when we go through and change the direction of the reaction, where does the energy term show up?
With the bond.
With the bond. It's now on the reactant side of the equation, which means to break the bond, I have to add energy. Okay? All these terms of adding energy or removing energy, releasing energy, aren't sciencey enough. So being sciencey, what are we going to do? When we add energy, we name that reaction as endothermic. Were you just doing the 50-50 after hearing the exo? It's not a bad idea. If we release energy, we've got exothermic. Okay? So it's just a question of kind of applying those relationships and seeing what happens out of it. We can then drop in a whole bunch of text and look at all that fun stuff coming out of this and all that fun stuff. Okay? Bond energy. Okay? So if I look at this new process, let's say to make the HCl bond, that energy released almost always is a form of heat. Let's say it's 5 kilojoules. If I now want to break that bond, how much energy do I have to put in?
5 kilojoules.
Why exactly 5 kilojoules?
That's the amount that
because that was the exact amount that came out in the process of making it. So to reverse the reaction, I have to supply the exact same amount of energy that was exchanged. As long as I've provided that exact same, I'm fine.
Kilojoules quite a bit, isn't it?
Yeah, it probably is. I just picked a random number.
Okay.
Okay. Now, getting into the kind of our strict nitty-gritty of ionic versus covalent bonds. Okay. So already we can answer this question. Are all bonds the same? No. Okay. There's really three classes of bonds: ionic, polar covalent, and non-polar covalent. When it comes to nomenclature, we treat polar covalent and non-polar covalent as the exact same thing. We do not distinguish between them. Okay, so they are named the same. Our ionic bonds are then named as a separate class. But within these, we now have to understand how can we define each of these different categories so that if you're given a bond, you can now say that's an ionic bond, that's a covalent bond, or that's a polar covalent bond. Because being able to identify the type of bond drastically changes your interpretation of what that bond can now do, both its reactivity and its physical properties. So we've got three examples here. Sodium bound to chlorine is an ionic bond. Hydrogen bound to chloride, polar covalent. Hydrogen bound to hydrogen is a non-polar covalent bond. Right? How can we distinguish between those so that every single time I give you a new bond, you can now tell me it's ionic, polar covalent, or non-polar covalent?
Which atoms are being bonded?
Okay.
The metals or non-metals?
H to O. Ionic, polar covalent, non-polar covalent.
Polar covalent.
H bonded to C. We need some way to define these. Okay. How do you know it's an ionic bond? Our definition that we've been working with is a metal and a nonmetal. That works for pretty much everything that you'd be looking at. Is there a stricter definition? Absolutely. Okay, that stricter definition you will probably have to use for your homework. Okay, and that stricter definition has to do with this little symbol right here. What's happening there? According to your homework, I think they actually use 1.8. What is that 1.8? I'm gonna let him finish. Can't get the term? It's the difference between electronegativities. Okay? When we're looking at our ionic bonds, it's a metal and a nonmetal. Well, our difference in electronegativities between both any of our metals and any of our nonmetals is massive. That massive quality is really about a difference of 1.8. Okay? If we are bigger than 1.8 when we look at that difference, it is an ionic bond. Okay? Are there gray areas where you can get a metal and a nonmetal that's less than 1.8? Yeah. And depending on what you look at, they may classify that as a different bond, which is a load of crap. Go based off of metal and nonmetal. Okay? If you get marked wrong on the homework, then you go through and look at the strict electronegativities. And after I answer this question, we'll explain why we want to do that.
What about metalloids?
There's electronegativities for them, so that definitely makes it harder to classify, but you would do based off of their strict electronegativity differences. Why do we say go based off the metal and non-metal and not based off their electronegativities? What's the electronegativity for fluorine? Okay, electronegativity for hydrogen. Okay. I was actually hoping for fluorine no one would answer, okay, because we had just talked about that one, and I kind of figured you would have already forgotten it. Okay. Nobody has the electronegativities memorized. Okay. It does not make sense to go through and use the electronegativities because that means you have to do a secondary step of looking up some extra information to go through and do that differentiation. So you need something faster. That's where metal versus non-metal can help. When should you be expected to go through and evaluate these strictly based off of the electronegativities?
Final.
Nope. Final, it's actually easier than that.
Oh, really?
If we give you the electronegativities, then and only then should you be evaluating the difference in electronegativity, because you are not expected to have those memorized. So if you are given then you can apply that information. If you are not given, don't apply that information. Go based off of the raw definitions. Okay? So metal and nonmetal. What's our definition for a covalent bond? Two nonmetals. So our polar covalent bond will have two nonmetals. A nonpolar covalent bond will have? Is that definition going to help us differentiate those two? No. So we need something better. Okay. What is polar referring to? Charge, ultimately. It's a balance of charge within our structure. When we look at our ionic compound, what did we say was the difference in electronegativity between the sodium and chlorine? Massive. What happens to the electrons in that bond?
A lot.
They spend all of their time
In the non-metal.
on the nonmetal. So chlorine takes the electrons and it becomes negatively charged. Sodium loses the electrons and it becomes
Positively charged.
positively charged. What do we have in this situation? We have a polar bond. We have a positive and a negative. When would we have a nonpolar bond? When the electronegativities are exactly the same. So if I give you carbon bound to carbon, nonpolar. Fluorine, most electronegative element on the table, bound to fluorine, nonpolar. What if I give you carbon bound to hydrogen? Carbon bound to hydrogen is the one extra thing you must memorize with your nonpolar covalent bonds. Your nonpolar covalent bonds, as a general trend, I don't have a better way of labeling this, same bound to same and carbon to hydrogen. Right? Are there other cases that fall in this category? Absolutely. You look at the raw electronegativity differences. If the difference in electronegativity is less than 0.5, it's nonpolar covalent. Why do I roll my eyes every time we look at those raw electronegativity differences? Depending on what textbook you use, depending on what edition of the textbook you use, they change the numbers. Okay? So it is pretty meaningless to evaluate bond characteristics based on the difference in electronegativity. Okay? So we now have a way to distinguish our nonpolar covalent bonds away from our our ionic bonds. So how do we go ahead?
Figure out the electronegativity of an actual bond itself.
You never find the electronegativity of a bond. Electronegativity is defined by an atom. What you can define is the difference in electronegativity between the atoms around which the bond is centered. So what's polar covalent?
Greater than 0.5 or less than 1.
So one definition, if our difference in electronegativity is greater than 0.5 but less than 1.8, cool. How many of you had your electronegativities memorized? No, you don't. Put your hand down. Okay? That's a pretty meaningless definition, so we need something else. That's the same definition for nonpolar covalent.
Two different nonmetals?
I would expand it a little bit more.
Different element? Two different electronegativity. We gonna play big man?
Damn, you're good. Everything else, simple as that. Is it ionic? No. Is it nonpolar covalent? No. Guess what it is? It's polar covalent. We don't need any extra definitions for that. It's everything else.
So what's the name of the combination?
Okay? So, as our quick examples that we pulled through, I shouldn't have erased that. Oh well. You remember that said everything else. Carbon to hydrogen. Nonpolar covalent. All right, that fits under that definition. I know, it's one of those extra ones you have to remember. Carbon to carbon. Carbon to oxygen.
Polar.
Nitrogen to oxygen.
Polar.
Hydrogen to oxygen. Sodium to sodium. That was a curveball, sorry. That's actually a metal to a metal. That's technically classified as a metallic bond. We don't have to worry about those. We don't have to worry about those for this class. All we're really going to deal with is ionic, polar covalent, and non-polar covalent.
How many different types of bonds is there?
Depending on who you talk to and what they classify as a bond, a lot. Okay? So those are your bulk categories as far as identifying things. What characteristics come out of this? Well, in an ionic bond, we have a positive and a negative. So what do we expect to see near the positive? What should be near a positive?
An element.
You can give me more information than an element. What should I find near a positive?
One with the lowest electronegativity.
More positive. Okay, let's work with that. I take a positive, I bring it near another positive. What happens?
They separate.
They repel. That didn't work. Try again. Find a negative. You got a positive. What comes near it? A negative. Right? If I now go through and take a look at my nonpolar covalent, what charge builds on the hydrogens? No charge. Equal sharing of electrons. There is no charge building on those. Okay? Would I expect to see any atom particularly attracted to those? Everything strives for lower energy, which is neutral. Are we already neutral?
Yeah.
Are we already low energy?
Yeah.
There's no reason to interact. For an ionic bond, we've got charges. That positive charge needs to neutralize. So what needs to come near it? A negative. So we will see a strong attractive force between that positive and any other negatives. In the case of the nonpolar covalent bond, there's no reason for it to interact with anything else. So we get virtually no interactions. What happens when we move to the polar covalent bond?
There's a negative and a positive.
Sort of. It is not formally positive and not formally negative. Why?
Positive one side, negative on the other.
Nope.
It's an enigma wrapped up in a conundrum.
Nope. For it to be a positive and a negative, what had to happen? You had to be an ionic bond. For it to be an ionic bond, what did we have to have? A metal and a nonmetal. Do we have a metal and a nonmetal? No. So we cannot have a positive and a negative because it's not an ionic bond. But we cannot be exactly neutral because it's not a nonpolar covalent bond. So what's happening in this weird gray area?
Science.
Yes, science is happening there. Which atom is more electronegative, hydrogen or chlorine? Chlorine is more electronegative. Okay? So what does that mean it's doing to those electrons? It starts to take them. It can't formally take them away because it's still a covalent bond, but it starts to take them. Okay? If it starts to take them, what charge does it start to become? Negative, because it's starting to take those electrons. What happens to the hydrogen? Starts to become positive. But if I draw it out like this, HCl looks an awful lot like NaCl. And those are two different bond systems. So I can't draw this, but I still want to imply some of that information. So what's the special symbol for starts to become?
Positive, negative.
What symbol is that?
S.
It's a lowercase delta. Mine may look crappy, but that's what it is. What did delta mean? Change. Okay, actually we didn't talk about what delta meant in this class yet, have we?
No.
Sorry, that was a different class. Delta means change. Okay? It's typically capital delta in reference to temperature, as in adding heat.
But it's a triangle.
What's the delta? That's capital delta. This is lowercase delta. Lowercase delta is going to mean the same thing. Okay? It's a change. That change is saying that this chlorine is changing to become negative. It's not formally negative because it's bound to a nonmetal. Why does this help us out? Why does this allow us to predict something about the difference in chemistry? The hydrogen found in HCl is what charge? Partial charge. Starting to become positive, which means what should we find near it? Starting to become negatives. If we take a look at the hydrogen in our nonpolar covalent, neutral, is there any reason for it to interact with anything? No. What ends up happening? We see an increase in reactions as we move from a nonpolar covalent compound to an ionic compound. As we add in more charge, we increase the likelihood of that reactivity. Why? Because we start to become more and more charged. Amazingly mind-blowing how sort of simple this is. We're looking at just differences in electronegativity and just defining what a bond is. And based on that definition, we now are able to predict something about reactivity. We can take it further and look at boiling points, melting points, solubilities, densities, all based of just identifying what type of bond it is. Right? And all of that determination ultimately came from looking at differences in electronegativity. Massively important. We will keep coming back to this because it is that important. At this stage, what you need to be able to do is to acknowledge all of these different representations. Okay? How do you classify a nonpolar covalent bond? Polar covalent bond, ionic bond. How would you draw a polar covalent bond where you can include that symbology that it's starting to become charged, that it's starting to become reactive? Those are your delta symbols. How did we know that chloride was starting to become negative and hydrogen was starting to become positive? What we remember is the trend in electronegativity. Fluorine is the most electronegative. Cesium is the least. Which is closer to the fluorine? Chlorine or hydrogen? Chlorine. Which one's more electronegative? Chlorine. So the trend is very important to pick off the electronegativities, not the values. Okay? Questions? Okay, I can't tell if you're all lost or if you all think this is really boring.
Yes.
I'm hearing some really boring. Okay, exciting. Let's make this more challenging. Lewis structures.
Yeah, yay.
Okay. Lewis, famous chemist, around the turn of the century, or 19th, 20th, 1900s, was looking for a model to try and explain chemical bonding. Okay? And his theory was based off of valence electrons. So our valence electrons are electrons at our outermost energy level. So our carbon has how many valence electrons? So we look at carbon. How many valence electrons does carbon have? Carbon is in the second row, which means we're looking at that second energy level. It's in which column?
2.
It's in the fourth column, which means it has 4 valence electrons. 2 of those are in a 2s, and 2 of them are in a 2p. Okay? How else do we know it has 4 valence electrons? Take a look at the top of the column, right above carbon. You see a 14, and then you see a Roman numeral 4. How many valence electrons does nitrogen have? 5. What's above nitrogen?
5.
A 5. Any guesses how many valence electrons oxygen has?
6.
Why?
Because science.
It says the Roman numeral 6 right above it. So those columns will tell you information about how many valence electrons you've got. So what he was looking at is simple molecules. So we got a whole bunch of simple molecules here. And he started to try and pick up some patterns. Okay? So we could go through and look at the electron configurations for each of these things. And within those patterns, he noticed that we could get up to 4 different things around an atom, okay, in the case of methane. He took that a little bit further. He said, well, 4 different atoms would be, 4 different groups would be what shape? What shape has 4 different sides?
Square.
A square, okay? But all of our atoms are what dimension? 3D. So while the square does kind of give us that idea, it's not quite giving us the proper geometry of this. So he also went through and looked at the number of electrons in that row. And how many electrons do we have in that second energy level? 8. Said, okay, I need to think 3 dimensions. What 3-dimensional shape has 8 points? 8 points. Most people have a hard time with it. I keep getting octagons. No, that's 2-dimensional. We're looking at cubes. Okay, this is literally how we went through into this. So we said we take these 2 cubes. These cubes represent an atom. Okay, so in this case, I'm taking a look at hydrogen, and I'm looking at that bond to nitrogen, it looks like. And what he went through and did is said, okay, each of those 8 points represents one of the locations that we can put an electron. Okay, and since there's 8 columns, we could figure out 8 places to put electrons. So we can put in an electron for our hydrogen. Just has that 1 electron for our hydrogen, right? Then he went through and took a look at the nitrogen. So, well, the nitrogen's got 7. That's not nitrogen. That's what element? What element is going to give us 2s2, 2p5? Fluorine. 7 points that need to be filled. So he went through and he filled in his 7 points of that. So, well, those look kind of close. What happens if I now bring these 2 near each other? This one can now exist there, this one can exist there. And what do we have? A bond. Every single one of his things he went through and dealt with cubes. God, that's an awful way to look at this. Because that means we're taking these nice, simple 2-dimensional objects, and we now have to draw them as cubes to look at our shapes. Everybody looking forward to that idea?
Yeah, I'm not sure about that one.
Okay, that's probably not our best option. So what do we end up doing? No. We're going to take those cubes and we're going to shrink them down into 2-dimensional objects because we draw everything in 2 dimensions. What's the 2-dimensional object for a cube? A square. Whoa. Oh, no, that worked. So we take a look at hydrogen as a square with 1 electron. We can take a look at our fluorine as a square with 1 electron. And what he ends up doing is now looking at where can we put electrons on any given face. These electrons can exist in between there. The rest of the electrons are now scattered around each of those atoms. This gets further devolved into what we typically see. Now, any place that I have a pair of electrons between atoms, those electrons can now share with the other atom, meaning those electrons have now become involved in a bond. Let's make sure our electrons look different. How can I make sure the electrons look different from electrons that aren't in a bond? What do I now have? The Lewis structure for HF.
What is HF?
Hydrofluoric acid or hydrogen fluoride, depending on what state you're looking at. We now have explained the bond that we see for HF. Hydrogen typically carries 1 bond. Fluoride typically carries 1 bond as well. We now have a way to explain that based off of his theory. Pretty bizarre how we came through and dealt with this and then what we simplify it all the way down to. Okay? There are strict rules that you should be applying when you go through to try and draw Lewis structures. Okay? Nobody seems to like the rules. Okay? And everybody seems to come up with new rules. I will tell you right now that the rules that I have listed here, I have listed for a reason in the particular order with the particular directions. Your textbook uses a different sequence of rules. The tutors use a different sequence of rules. Future faculty will use a different sequence of rules. All of their rules are horrible. And that's not just because I think I'm better than them, because they're probably better than me. But when it comes to Lewis structures, I'm better than them. These rules are written out in this fashion and designed in this way to allow you to discover certain things, or let the structure discover certain elements for you instead of you having to guess your way into them. The biggest one is right here at the end, resonance. Arguably the most important concept for organic chemistry. Right? We talk about it a little bit, but we kind of just leave it floating. Okay? As you move through more chemistry, you may see more rules added on top of this. Please be aware. Okay? This is a time when I need to talk to the tutors to make sure they're aware of this. The rules for chem130 are different than the rules for chem151, which are different than the rules for chem152, which are different from the rules from organic. That means if you ask for help from a tutor, they may very well take you to a structure that you have no understanding of how to get to. If they take you to that point, and you provide that as an answer, you are wrong. You have to follow the rules to the understanding that you have. So when it comes to an exam and I ask you to provide a Lewis structure, it turns out that in multiple cases there are multiple different answers. If you provide me one of those answers that does not follow this set of rules, what you will get from me is a new problem that I will ask you to solve directly in front of me. If you get that problem correct, I will give you points. If you get it wrong, I remove points. Okay? Because you have to understand how and why you draw the structures as you draw them. If you do not understand that why, I will not give you the points. Okay? I hate to be really soapboxy and yelly about this, but it's just really important to me. So let's walk through these rules. Total your valence electrons for every atom. Okay? We already talked about doing this. Carbon had how many valence electrons? 4. Nitrogen. Fluorine. 7. Oh, beryllium. Jeez. 2. Beryllium has 2. Be. Arsenic has. That might be cheating. Do we need the symbol for arsenic? Arsenic's symbol is As. It has 5 valence electrons. All you're going to do is look at that column. Okay. The next part of this is count charges. If you have a negative charge, what does that mean? True, it's probably a non-metal, but how do you get to a negative charge? What has to happen? You have to add electrons. So if you look at a formula that has extra electrons, has a negative charge, you need to add more electrons to your total. If it says -1, how many electrons do you add? 1. -5. 5 electrons. Just add it up, put it in. What if it's a positive charge? You have to remove electrons. So when you're looking at your total count, just subtract an extra electron to account for that charge, okay, that positive charge. You'll then need to choose a central atom. You will be doing an activity in lab, unfortunately, probably after the exam, okay, that has you go through and do a variety of these. Okay? The central atom, at least as far as this class goes, will be your least electronegative element that can bridge. So to bridge, it has to be able to bond at least twice, because it has to grab a couple other atoms and connect them and act as a bridge. So can hydrogen ever act as a bridge? No. Can halogens ever act as a bridge? No. Okay, well, you run into exceptions which we won't worry about. I'll leave that to worry about for your lab. Okay, so we pick the least electronegative atom that can bridge, and then what we can do is scatter the other elements in our formula around that central atom. Okay. After that, we then want to start adding electrons into our structure. We'll add those electrons in pairs. Why do we add electrons in pairs? Where do electrons exist? Not quite accepting pairs, but kind of the right idea. Clouds, getting closer. Orbitals. How many electrons fit in an orbital?
2.
2. That's why we add it in pairs. Okay. We will add them in pairs around what atom?
Central atom.
Nope. This is the biggest distinction from your textbook. You put it around the most electronegative element. Why?
Because it's the one that takes it.
Electronegative elements are the ones that are going to take the electrons. So we want to put our electrons around them first because they are the most electronegative. They are grabbing the electrons. Okay? We need to add them until they satisfy the octet rule. Any guesses what the octet rule means? Why 8 electrons? Because oct means 8. Okay? There's a nice simple answer. Why else? Look at that second energy level. How many columns do we have? 8. There's your octet rule. It's satisfying the energy level. Okay? You'll continue adding electrons around your progressively next most electronegative element until you've added all of your electrons into your structure. Okay? How many electrons do you have to add? You add enough electrons that you reach the total valence that you did at the very first step. Once you've achieved that, you've now got your proper electrons in there. Okay? Then what you can go through and do is simplify. Any place where you have a pair of electrons between atoms, you can now convert into a line. What does the line represent? A bond. Where should you draw lines? Only between atoms. If you talk to really old chemists, what they will do is show a line for every pair of electrons. Okay, I don't like that. Let's show a difference between a bond and not a bond. Okay? And this is really only old chemists. Hopefully your lab instructor isn't that old. We'll see what happens. The next part is step 6. What we'll do is move electrons between atoms that have not satisfied their octet. So everything needs to have 8 electrons around it. So if for some reason we have an atom that does not have 8 electrons, we'll have to move electrons towards it to satisfy it. Okay? In the process of moving those electrons towards it, we will not rip them from one atom and place it on the other, because then what happened? Not only does it change the charge, the other atom now doesn't have its electrons. It's now missing its octet. The only place where we can satisfy our octet is by moving electrons into a bond. So you'll end up making more bonds between atoms. If there's multiple ways that you can move electrons, then you have this concept of resonance, which is a mind meld on its own, which we'll worry about. Meld is the polite way to put it. And then we can go through and assign formal charges. The formal charges is the biggest step for you guys that you do not really have to do. Okay? All you have to do is say, if the structure is charged, upper right-hand corner, you write a little bracket and you put the charge. Nice and straightforward. Okay? You are now all experts at Lewis structures, right?
Yeah. Yeah, sure.
If you're really going to accept that, and I won't do any examples. Should we do some examples?
Yes, please.
Let's take a look at, I'm going to do one really fast, and then we'll give you, well, I'll do 2 really fast. CF4. Step 1. Total the valence electrons. How many electrons does carbon contribute?
4.
How many electrons does fluorine contribute? 7. So I just add that up and I get a total of 11, right?
No,
What's the no?
because there's 4.
There are 4 fluorine atoms. I can't do that math. Someone help me.
28. I just did this.
Stop it. 7 times 4 is 28. Plus 4 is 32. I just do the math, not confuse me. I've already seen I'm already messed up. Okay. Central atom is our least electronegative that can bridge. Only a few atoms cannot bridge. Right? Which is lower in electronegativity, carbon or fluorine? Carbon. So carbon is going to be our central atom. We will now scatter the fluorine atoms around the carbon. Lewis structures were based off of what shape?
Squares.
A square. So in the process of scattering our fluorine atoms, I'm going to scatter them according to the square shape around the carbon. Fluorine, 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 fluorine. Now what do I do?
Show the electrons.
Start adding the electrons. Where do I add the electrons first? To the fluorines, or our most electronegative element first. Which fluorine is most electronegative?
All of them.
Doesn't really matter, they're all the same. So let's just start adding. There's 2, 4, 6, 8. Why 8?
Because carbon has 2.
Octet rule. 2, 4, 6, 8. Octet rule. 2, 4, 6, 8. 2, excuse me, 4, 6, 8. We've now added all the electrons. Or, well, I've added 8 electrons to each of the fluorines. 8 times 4 is 32. Can I add any more electrons to my structure? No, I'm done. Okay, as far as that step is. Next part is to convert pairs of electrons into a line. Remember, this is only between atoms. Where do I have a pair of electrons between atoms? There's one, there's one, there's one, there's one. Satisfy the octet by moving pairs. So now we've got to count electrons. How many electrons are around this fluorine? 1, 2, 3, 4, 5, 6, 7, 8. Around the other fluorine. Carbon.
4, 8. There's 8.
What does this line represent? What is this, just this line? 2 electrons. And it's 2 electrons that are shared between carbon and fluorine. Okay? Which means that carbon has access to both those 2 electrons. Which means it has access to those 2, and those 2, and those 2, which comes out to 8 total electrons. Carbon has its octet satisfied as well. All of our atoms have their octet. We have no resonance. As far as formal charge, that's your official rules on that. Is our structure charged? How do we know it's not charged? What's written in the upper right-hand corner of our formula? Nothing, which means there is no charge. There's your structure. I would highly recommend you take a stab at those last 3. See what you can come up with those before Thursday. We will be going through and dealing with those 3 on Thursday, which is going to touch on resonance and all the formal charge rules. And Don, I see